Hi guys! Today we are actually going to learn about different types of distribution because we learned about normal distribution and how to describe a distribution in general. But there are two special distributions. So the first one is called the Poisson distribution. And this one is very interesting because this is a probability distribution for an event occurring x times over a given interval. So, like how many times will you see a firefly flying by in like an hour or so? So that kind of thing. It's a very specific. So the example they give you is such as the number of people entering a store during 1 hour, right? Obviously, if you're like a store owner, you want to determine like how likely it is to have like a surge of people coming to your store. This distribution is quite important, right? And because you're counting how many times it's happening, it's a discrete variable, not continuous variable. So in that sense, it's kind of similar to binomial because binomial is also discrete. The probability of an event occurring x times over a given interval is this funky looking equation. So this symbol is called lambda, right? Lambda to the x power. So lambda is average number of times that event occurs in a given interval, right? And x is like how many times that the time that I'm interested in knowing. And e is the e that you know. It's the Euler's number. It's like 2.72, right? And then negative lambda over x factorial. I know, it's kind of crazy looking. And obviously, like, even for the quiz, you will have this next to you, so you don't necessarily have to memorize. As long as you understand how the factorial works, that you know that e is a number, and lambda is a new kind of like a number. It's like it's mean, basically, right? So the distribution looks like this. This is just like a random Poisson distribution. So if lambda is 1, obviously you can see that it peaks around average of 1, right? And if lambda is 2, it peaks over 2, 3, 4, and you can see how it's getting flatter and flatter because you want to hit the mean at where lambda is. So the center is always your lambda, and the distribution is pretty even around, like even, what's the word? Even around that lambda value. So let's look at how we might be able to solve these problems. So let's read the examples together. A bank manager determined that an average of 9.2 customers use a certain ATM every hour. So then lambda is 9.2. Oh, that's not what I wanted. Okay, 9.2. And it says, let's say you want to find the probability of 5 customers using the ATM in a given hour. How likely is that? So then you plug in the equation right here, the formula. So lambda was 9.2, and then x was 5. E to the negative lambda over x factorial. That's exactly what you did, and you got P of 5 being 0.055, meaning 5.5%. So there's about 5.5% of 5 customers using this ATM given hour. And there is, just like a CDF, as a normal binomial PDF, there is a Poisson PDF, which is given that specific value. So if you do Poisson PDF, lambda, comma, x, then it will give you, basically, it's running this formula and spitting out the answer. Okay, so let's look at number 1. The bank manager determined that an average of 1.8 customers inquire about opening a new account. So lambda here is 1.8. And we want to see how likely all these things happening. And interesting enough, your average number doesn't have to be a whole number. Even though we're talking about the discrete values, just like your expected value for binomial distribution didn't have to be a whole number. So you go to distribution, which is second worst. And if you go down, and go up, then you will be the bottom of the menu. and you choose the Poisson PDF. Lambda is 1.8. And I want to know for 0 for the first one. And the value is 0.165. So I will keep 3 digits. And I'm not going to show you on the calculator. I'm just going to do it on my calculator so that I can cut some time here. So try them and then we'll see. And these are the values I got when I typed it all on my calculator. And as you might have guessed, that it's highest, the probability is highest for 1 and 2 because your average is 1.8. So you're assuming that your graph will look something like this, right? Where this being 1.8. Alright, let's look at number 2. Notice that unlike a binomial distribution, x has no upper limit. Oh, so this is a huge difference for x because you could possibly have a really large number. What if something happens that you never expected and on average you get 1.8 customers, but maybe like 100 people came. It's very unlikely, but it is possible, right? And so that's why there is no upper limit on x for what's it called? The Poisson distribution. So here it says the table in exercise 2 stopped at x equals 5. I think that's exercise 1 actually. But it is possible for 6 or more people to inquire about opening a new account. How can you find x is greater than 2? So think about this. X is greater than 2 is same thing as 1 minus p of x 0, p of x equal 1, and p of x equal 2, right? Because my probability, even if it can go to infinite, your area under curve is always 1. So basically, if I do 1 minus 0.165 minus 0.298 minus 0.268, this will give me a probability of what's happening for the rest of the numbers. And it's 0.269, so it's not a big, big probability. So 26.9%. Okay, so the probability that more than 2 people will come to this store would be 26.9%. Number 3, on average, the bank receives 4.2, meaning the lambda is 4.2. And this one, x is 3, x is 4, x is 5, x is 6, and x is 7. Why don't you stop the video, try these numbers for yourself using the Poisson PDF, not CDF, because CDF is cumulative and PDF is probability for that number. And then, so stop the video now and then try them and we'll compare the answers. Okay, so these are my answers, the green. Hopefully you and I both got the same thing. And so that's the Poisson distribution. I hope, even though like there are new variables and so forth, that it's not very hard for you to try the problems. Another distribution that I wanted to introduce you to is called t-distribution. So t-distribution, you use it whenever your sample size is very small. So if you remember the central limit theorem, that you have to have a large enough samples to assume normal, right? And so what if you have a sample size that is small, like 10 or 5, right? Then what happens is that you can use t-distribution, assuming that there is no strong outliers or skewness, okay? So it is still important that your individual data, when you make a histogram, it looks mostly symmetric and no outlier. But t-distribution, the relationship that t-distribution has with the normal distribution can be seen in this graph. So the z-distribution, which is a normal distribution, it's a lot skinnier with like a peak at the mean, right? And the mean, so the center is also the mu, which is your x bar, for the t-distribution as well. So mean is always where the peak is. T-distribution is actually a lot wider looking than the z-distribution. The reason why is because, we'll get to that a little bit later. Because also your population standard deviation is unknown. That's also why. Okay. And in real world, you will really never know the population standard deviation. Okay. So like all the problems that you have solved so far for Z is very idealistic. It actually never happens, because think about it. You want to study your data to infer about population. So if you already know the population standard deviation and mean, there's no need for statistics, right? You already know. So t-distribution is often used more, even though normal distribution is so nice because all the formulas works and all that. So you can tell the n, your sample size, if it's smaller than 30, then it's not as extreme as this one, but you can tell that it gets wider. Okay, it's wide around the peak, and as it gets closer to 30, because we said 30 is a big enough sample size, then it gets closer and closer in its shape with the normal curve. All right, so there's a new thing called degrees of freedom. This concept is a little bit more tricky, and I don't think I have a very good way to explain it. But the degrees of freedom is necessary for you to know which t-distribution you're looking at. And this is always found by one smaller than your sample size. So if your sample size is 5, your degrees of freedom is 4. And this is the t-distribution you're looking at, because every t graph looks different, depends on your degrees of freedom. Okay? Yeah, and then just like you found z-score, there's such thing as a t-score, because remember, z-score is basically how many standard deviation you're away from the mean, and the t-score is the same thing. T-score is how many standard deviation you're away from the mean as well in the t-distribution. And so it's always the sample mean, it's the sample size, but it's a sample mean minus the population mean over your standard error. So the z-score was found by sample mean minus population mean over standard deviation sigma, right? And t-score, you are going to always do standard deviation divided by square root of n. Okay? And that's it. I think the problems related to t-distribution is related to actually confidence interval and hypothesis tests, which I don't think we're going to really go into that because... or like a not in depth. Okay. That's it. That's it for today. I just wanted you to know that there are more than normal distribution. Normal distribution is the ideal, basically ideal world, but there are many other distributions. So like a chi-square distribution would be another thing that you might come across, especially if you do biology, I think. But I don't think it was in your textbook, so I didn't go over it. But Poisson distribution was actually in your workbook, and I thought it would be nice to know other distribution. Because in AP, you don't actually learn about Poisson distribution, but I remember learning Poisson distribution in my statistics class, and also a probability class in college. So I just wanted to introduce this to you so that if you need it for whatever reason, that when you're doing research or things like that, you need to use a distribution that is different from a z distribution or t distribution, that you know that this is available if this situation is something that you are studying about. And that's it for today.